1:48, it's time to get going.
Oh, okay, all right, watch out there. Love the color.
Oh, so, yes, now it's pointing only here, but if you want. All right. All right. So yes, our next speaker is Mohammad Nezhad. His lecture is improved effective Łojasiewicz inequality. Polynomial optimization.
All right, thank you. Thank you for the introduction and thanks to the organizer. So this is the topic of my talk, improve effective Łojasiewicz inequality. I'm going to talk about its semi-algebraic version and also the application to polynomial optimization. And of course, this is the joint work with Professor right here. So this is the plan. So I'm going to talk about the Łojasiewicz inequality, but I also try to keep a concrete example, which is polynomial optimization. And then we will talk about the semi-algebraic version of Łojasiewicz inequality. And you will see the direct application of Łojasiewicz inequality. And then at the end, I'll try to cover a little bit of the ideas of the proof that we have here. So what is the goal here? The main goal of the talk is to show you that if you want to think about computational complexity in optimization, Łojasiewicz inequality is a great tool here, and you will see Łojasiewicz inequality quite natural in optimization. And for that purpose, I have a concrete example. It's called polynomial optimization. Perhaps it doesn't need much introduction. So you are minimizing a function, which is a polynomial, over the so-called basic semi-algebraic set defined by polynomials, which has been introduced here. And so there are some classic facts about polynomial optimization. Of course, if you know about linear optimization, this is much harder. So we don't have like efficient, fast algorithms to solve it. And if you also want to try symbolic algorithms, there is no polynomial symbolic algorithm. So the best complexity that we have is going to be singly exponential in terms of the degree of polynomials, the number of polynomials here, which forms the basic semi-algebraic set, and of course, the number of variables here, right? So this is the best we can do to represent solutions if there is a solution here, right? And like I said, there is no efficient numerical method for polynomial optimization in general. So the question is, this is a hard problem. How do we solve it, right? So we have a great algebraic structure here, but we can use also algebraic tools to solve this problem almost efficiently. And the tool that already exists in the literature is called sums of square relaxation. So what is sums of square relaxation? Let's start with a polynomial here of even degree, right? We know from the fundamental theorem of algebra that this polynomial is non-negative if and only if there is a sums of square, there is a representation of the square polynomials here. So if you can do that, we have an if and only if relationship between these two. And it turns out that the answer to this question can be found out very efficiently using optimization. The tool that we have here, so I mean, you only need to do some bit tricks here to convert this problem into a semi-directive optimization problem. So all you have here is a set of affine constraint subject to a positive semi-definiteness constraint, and this M is basically formed by the coefficients of the polynomial. So if there is a solution to this problem, it means we have a sums of a square representation for the polynomial, and it means it's non-negative, right? And this we can do this quite efficiently using current numerical methods, right? But this is perhaps not very useful because it's just talk about one polynomials, but perhaps a greater use of tools in real algebra helps us solve this problem directly. So now we are targeting the same polynomial optimization problem, and this is a fact here that if f is positive on this basic semi-algebraic set, then there is another representation which almost looks like a sums of square representation. So you have a polynomial here, which is sums of a square. You have ui, which is sums of a square, and this gi are the polynomial forming the semi-algebraic set here, right? And we can also solve this problem using semi-definite optimization. So, but it's not doing a magic here. So you are going to solve a sequence of semi-definite optimization problems. It only gives you a sequence of values. It doesn't guarantee that I'm giving you exactly the optimal solution of polynomial optimization, right? So it doesn't, it's not a magic, but there is another result here which we care about in this talk here, and that's about the convergence of these hierarchy. So if you are solving a sequence of optimization problems, it's going to converge to the actual optimal value with this rate. And there is something here, there is a quantity here, which basically depends on this inequality. And this is the inequality which actually brings us back to Lojasiewicz inequality. So if you know something about this quantity, we can also talk about the speed of convergence, right, for this procedure. So I'm not going to talk about sums of the squares. I'm just giving it to you as an example, and just to convince you that Lojasiewicz inequality has deep roots in optimization, right? Okay, so like I said, okay, what happened? Okay, so like I said, the last convergence rate depends on a new notion, which we call error bound, the previous inequality. Maybe I can formally define it here. So if you are given a set like E and another set, which is not necessarily a semi-algebraic set, there is, if there is an inequality between the distance of a given x to m and another function, which we call a residual function. This function basically tells you whether or not you belong to the set. So if the function is 0, it means x belongs to m. If it's non-zero, we are outside that, right? So if there is an inequality like this with this row, we say that the error bound exists, right? And maybe we can come back to the previous example here. So in the case of sums of a square or polynomial optimization, our set M is just a set, the feasible solution, the set of feasible solution, and the residual function is basically, or the function that you saw on the right hand side is just measures the violation of x with respect to all these inequalities, right? And of course, this is not a polynomial, but it's a semi-algebraic function, right? Okay, so the great question is, okay, so we know about the error bound. The error bound, you will see that the error bound exists for case of semi-algebraic sets and functions. But what can be said about the magnitude of rho? So if you know the magnitude of rho, we can also say about convergence rate and perhaps other applications, right? And this is a classic problem. So what happens if M is a special? So normally we might think about general semi-algebraic, basic semi-algebraic sets, but if M is convex and defined by polynomials, the result would be interesting. For instance, if all the polynomials are linear or convex, rho is exactly 1. If you have convex quadratic, then rho is 2 raised to n minus 1, right? Or if we have convex polynomials, and this is coming from a result of polars, that rho depends on the degree of polynomials n, and you don't see any sign of cardinality here. And there is a most recent result, which basically contains all these algebraic and combinatorial parameters together. So it depends on D, depends on N, and depends on S. So that's not our work, but what we want to claim here that there is an upper bound, yes. These are inequalities. So, all right, yeah. So the question here that do we have a bound for general polynomial which doesn't depend on the cardinality or doesn't depend on S. Remember, S is the number of polynomials in our setting, right? And this is not the first time that we asked the question. This has a long history also in real algebraic geometry, which we will address later. But in order to address this question, we are going to stick to Lojasiewicz inequality and also tell you that the error bond that we just introduced is a special case of Lojasiewicz. All right, so I guess semi-algebraic set and function doesn't need introduction here. So let me just fix the notation. So we are assuming that, in the rest of the talk, we are assuming that we are given a P formula which defines our semi-algebraic sets and semi-algebraic functions. So we have a P formula for semi-algebraic sets, and we also know about their degrees, and simply in simple words, P semi-algebraic set defined by defined as follows, right? So this is our semi-algebraic set, and I always try to put this nice example from the VCR code. It's not a polynomial optimization because we have inequations or but that's a semi-algebraic set. And in the same way, we also define Q semi-algebraic functions whose graph are defined by Q semi-algebraic sets. So I guess this should be well established here. And we also have another notion which is closely connected to this, the topic of this talk, and is Tarski-Seidenberg. And again, another classic result, which means that the projection of a semi-algebraic set is again semi-algebraic. Or if you have a quantifier formula and try to eliminate quantifiers, you end up with equivalent quantifier-free formula whose realization is a semi-algebraic set. So this is a theorem, but there is also an algorithmic version of this theorem, which is called quantifier-free. And we actually used a great use of quantifier elimination to derive quantitative forms for Lojasiewicz inequality. Okay, now it's time to talk about Lojasiewicz inequality itself. So what is Lojasiewicz inequality? So suppose that two families of finite set of polynomials are given, one for the semi-algebraic set, one for semi-algebraic functions, and we are given a closed and bounded semi-algebraic set like A, and two continuous Q semi-algebraic functions where the zero set of F is contained in the zero set of G. And it turns out that if everything is semi-algebraic, there exists a positive C and an integer row such that this inequality exists, right? Now that you look at this inequality, you can also realize that this is almost the error bond that we defined, right? And if you are wondering about the row here, if you are wondering about the row in the error bond, you should be also concerned about the row in the Lojasiewicz inequality. Sorry, you have a question?
Why does this depend on this P and Q? It's too unrestricted. No?
I'm sorry, say again. This is say this.
I mean, the Lojasiewicz equality just goes on all closed subsets, on all closed semi-algebraic subsets. So I don't know why what's P and
Well, yeah, we define it that way because this is what we actually need later to derive quantitative ones. Yes, this is right. So we need this later because we assume that we have a P semi-algebraic set and function, right? Bounded by D, right? So if the Lojasiewicz inequality holds, the infimum of rho is called Lojasiewicz exponent. And previously, the best bound that we have is due by Salerno, which depends on D. D is the sum of the degree of polynomials, which shows technically that the bound here depends on the number of polynomials and the degrees, right? So we have both algebraic and combinatorial parameters and also n. So, but what we want to show that we can prove a bound which only depends on the algebraic parameter, not on the combinatorial parameter. And like I said before, this problem has appeared, this question has appeared in other contexts. For instance, if you think about the sum of the Betti numbers of semi-algebraic sets, there are bounds which depend on both algebraic and combinatorial parameters. or if you think about the quantitative pair selection lemma, is the work of Hugo Basu and Mary Francois, we can prove a bound which only depends on the algebraic form, which only depends on the degree of polynomial. Or also, if you think about the degree of polynomials in quantifier elimination, which has a direct application in this talk, it only depends on D or the algebraic part. So this problem has appeared before in other contexts. And now this is what we want to prove here, that for previous setting of Lojasiewicz inequality, there exists a constant, a positive constant, depending on A, closed and bounded set, and F and G are the semi-algebraic functions, and some N bounded by A times D. So D is the degree, and here we have like the number of polynomials such that inequality, right? And the great feature of this inequality is that it's independent of the cardinality of E and Q. So we actually prove something. So later you will see one of the great application of this independence in another proof. And I should also mention that this is not the first attempt to remove the combinatorial parameter from the Lojasiewicz exponent. Kolar also did this, but for a more restrictive setting. So maybe for another case of semi-algebraic set, but there were additional assumptions there. So I thought this needs to be mentioned here. And here you can also see another example by Kolar, which also tells you that the bound that we just provided is almost tight. So if you look at a disk as the set A, and this is almost a distance function, and another function which looks like the residual function that I introduced, right? So you can come up with a sequence of solutions, and if you do the math, you can realize that the Lojasiewicz exponent for this case should be at least d raised to n. And if you compare it to the bound that we provided, it's almost right. Okay. Now, I guess you immediately see the application here. Now we can come back to error bound that I just introduced, and I also told you about the special cases for convex polynomials, and now we can actually prove it for the case of semi-algebraic. So if set M and E are both semi-algebraic given by a set of a finite set of polynomials bounded by D, and also if you have a residual function defined by Q semi-algebraic set, then we can prove that the error bound exponent is basically bounded by D raised to n squared. So from n in the Lojasiewicz inequality, we actually ended up with n squared. And if you also have a further assumption that M is finite, you are getting a very good bound, as good as the convex case. So you are almost the same as Lojasiewicz inequality. Okay, so let me at the end of the talk, let me just talk quickly about the ideas of the proof. So the first thing which I would like to mention is the error bound exponent. So sounds like that this is an easy application of the Lojasiewicz inequality, because I mean, if I look at this, this is obviously a semi-algebraic function. This is assumed to be a semi-algebraic, so this we can set gx equals to the distance function, and we're done, right? So, but if you do this naively, you don't get up basically come up with the last one that I show you. You don't get up with this. You don't end up with this. And the reason is the following. So in order to apply the Lojasiewicz inequality to the error bound, I need to somehow represent the distance function using a formula, quantifier formula. And this is one way of doing this, by including all the needed quantifiers, right? And the problem is that our assumption is that we need quantifier-free formula. So you need to convert this to a quantifier-free formula. And if you try to get rid of two blocks of quantifiers, as you can see here, the degree of the formulas, those are exponential. So from D, which is the degree of polynomials here, you end up with n squared. So this is the complexity right after quantifier elimination. And if you give it to the formula that I just told you, you end up with dn cubed rather than dn squared. But we actually propose this as the error bound exponent, not the n cube. So what is the trick here? The trick is to redefine the distance function. So instead of just defining the whole formula in one shot, we try to define the distance function as the infimum of. So we need to define a set like W and look at the fibers over X, and that would be exactly the distance function. So the process that I'm trying to follow is giving you a huge, a long formula consisting of many polynomials. But the trick is that our Lojasiewicz inequality doesn't depend on cardinality. We don't care about the numbers. As long as we can keep, we can control the degree of polynomials, we are fine. So if we follow the approach, we end up, so we only need to do the quantifier elimination only once. So we end up with a new quantifier-free formula, which only, whose degree is only d raised to n. And if you follow the approach, we only need to apply the quantifier elimination twice. Once in the first step, the size of the block is n. The second step, the size of the block is 1. So we end up with d raised to n. And that would give us the better degree of the distance function. And again, we use the fact that the Lojasiewicz inequality doesn't depend on the cardinality of the set. All right. And maybe I can also, in how much time we have? Maybe one, right?
Not much, no.
Okay.
Over.
So let me just tell you very quickly. So this is also, so we talk about the error bound, but if you also wonder about the proof of the Lojasiewicz inequality, so there is a classic proof in the VCR book whose goal is try to show you that this is going to be continuous on n, on A, and that also means that the supremum of this function is attained on A. So this is our approach. So we are trying to define a set and then define a semi-algebraic function over this set, and the rest of it is the effective use of quantifier elimination to get a better complexity bound. So if we use a quantifier elimination, we get both goals at the same time. First, we can answer the quantitative part. That tells you that this Lojasiewicz exponent, it gives us the degree of polynomials, which later will be used for the Lojasiewicz exponent, and it also answers the existence part. So using the quantifier elimination again, and also some classic results in algorithmic real algebraic geometry, we can prove a growth. We can actually control the growth of this semi-algebraic function, and we already know about the degree of p. That would also imply that this function extended by 0 is continuous on A, and that also proves the Lojasiewicz. So I'm gonna end the talk with the last with one open question here. So we mentioned that the Lojasiewicz inequality that we proved is almost tight using the examples that I show you. But I'm going to use that example as well to pose another open problem, and that's the following: do we have, is the upper bound for the Lojasiewicz exponent is tight as well? So, or if you only focus on the error bound, the best that we can do is d raised to n squared. But the best example that we had is so far is d raised to n. So there is a gap from d raised to n to d raised to n squared, for which we were not able to find any problem. All right, that was all. Thank you. Thank you.
We're looking at the realist, right? Not our relative.
Say again.
In the theorem, where the estimate comes up, we're looking over the real field, not over the relative. This is for the real field or over the real field?
A real cosine. Is that your question?
This is a statement about polynomials.
Polynomials. Semi-algebraic stuff, right? So this is a theorem. Right, if I understood the question, right? This is a theorem.
This is over the real, yeah.
It's here. Yeah, this is a real cosine.
No, next slide. The one, yeah, this one. Which is over any real close to it.
Yes.
Does this have a real geometry? It's surprising that the relations.
For the Lojasiewicz inequality.
Quantify over
Well, so far we had applications for polynomials, which is defined over.
You check the number of polynomials here, and arguments that are polynomials.
So I mean, so we don't know about that.
Yes.
Normal can be able to speed this C.
All right.
Yeah, if we assume that these are our integers, then there is a double exponential bound on C. Right, but in general, we don't have bound on C.
All right, well, great. Thank you very much.